Okay, welcome PCS members and friends to our today's PCS IBS seminar. It is a pleasure to have with us today on site Dr. Yosep Kim from KIST, and our scientific host today is Kyung Min, and I would ask Kyung Min to introduce our speaker.
Thank you, Dylan. So it is also my great pleasure to introduce Dr. Yosep Kim, senior researcher at the Korea Institute of Science and Technology, who will be our seminar speaker today. So Dr. Kim's research interest in quantum information science and technology, specifically in photonic and superconducting systems. Prior to joining KIST, Dr. Kim completed his PhD in physics at Puang University of Science and Technology. He also completed postdoctoral research position at the Lawrence Berkeley National Laboratory in the USA, where he worked on the implementation of high-fidelity 3-qubit gates for superconducting qubits. Dr. Kim has made a significant contribution of the field to quantum information, and he also published several papers in highly respected journals like Nature Physics and PRL. So we are excited to hear more about his research today. So let's welcome our speaker.
Hi, I'm Yosep Kim. Thanks for giving me a chance to present my work. Actually, I'm a bit afraid of presenting my talk in front of theorists because I have a perception that theorists are generally harsh or tough. But I will do my best. So today I'm going to talk about how to extend quantum operation of fixed frequency superconducting qubit. As you know, these days, many physical platforms are competing toward practical quantum computer. As you can guess, I will focus on the superconducting circuit in today's talk. So I think most of you are not very familiar with the superconducting qubit. So I prepared some introductory slides. So I will give you the information that how the superconducting qubit is operating. So yeah, let's start from this. So basically, superconducting qubit is a superconducting circuit. So let me start from the LC circuit, which is the basic circuit element. So this LC circuit is composed of inductor and capacitor, and the resonance frequency is given as 1/4 scalar to LC. And the key parameter of this system is the magnetic flux and charge. And these two parameters are in conjugate relationship. So if we look into the Hamiltonian, you can find that the analogy with the XP system. So we can consider the charge as the momentum, and we can consider the flux as the position. So I will consider this flux energy as the potential energy. So if I draw the potential energy, then it has a harmonic oscillator shape, and it has a degeneracy in the energy level. There are two ways to drive the system. The first is the current, and the second is the voltage. And if we oscillate this driving source with the resonance frequency, then we can manipulate the system. So for instance, if we prepare the initial state as 0, then by this drive, we can excite this state. And at this level, there are two options that excite it more or lower into the ground state. So in the end, if we consider all contribution, then it will follow the Poisson distribution approximately. And this is not good for the quantum information science, because what in it is just a qubit, which is two-level system. So we need to give us some non-degeneracy to this system. And that's why we need the nonlinear circuit elements beyond the L or C. So this Josephson junction is the nonlinear element. And as you know well, this consists of the superconductor and insulator and superconductor. And if the insulator is thin enough, then this Cooper pair can tunnel the insulator and it make a Josephson current. And this Josephson current has this relationship, which depends on the flux difference of these two superconductors. So if we look into the Hamiltonian of this, before saying that, I will use this symbol, and this symbol represents the Josephson junction. And if I write down the Hamiltonian for this Josephson junction, as this is basically a capacitor, right? The metal and insulator metal. So it has a charge energy. And because of the Josephson current, there is a kinetic energy, Josephson energy. So as I said, I will consider this term as the potential energy. So if I draw the potential energy, it has a cosine shape. And obviously, it is not a harmonic oscillator, and it has a non-degeneracy. So now, if we drive the system with the 0 to 1 transition frequency, then we can manipulate it precisely. Yeah.
Sorry, I'm failing to understand. You say it's potential, so the current is quantized, or what is?
That's a good question. So basically, I cannot say this is the quantization of the current or charge, because as you know, if we second quantize the system, for instance, P equal A dega plus A, X equal A dega minus A, like that.
Yeah.
So this quantized, this quanta is a mixture of the current and charge in terms of the operator. Yeah, you can just consider this has a good analogy with the XP operator.
So you're claiming that it's mathematically the same?
Yes, mathematically same. So this is defined in the flux basis, and I would not tell each level, the quantized level is flux or charge. It has a wave function, like, you know, the first ground state, the ground state has a this shape, and first excited state has this kind of wave function, right?
And the phi x as well is phi x, or is flux? What's the role of the phi?
Phi is basically, you can understand this is the magnetic flux, which is applied to the circuit. And yeah, which is corresponding to the superconductor's phase.
You still have this commutation relation between Q and phi, right?
Yes.
I question how about in the circuit, the dissipation is not so quick.
Yeah, that's a good question. So basically, that's the reason why we are using the superconducting circuit to make a quantum system. So if it has a dissipation, then the coherence time of the system will be very short. So that's to avoid that situation, we are using the superconductor. But I would say this is not perfect, because if we put some driving line, then it works as the dissipation channel. So energy would go out through the line. So the coherence time or energy conservation is not perfect. So there is always trade-off. If we try to make a system very robust, then we lose the controllability. So we need to consider the trade-off between them. Yep. And so, yeah, if we add the nonlinear element when we compose the superconducting circuit, then we can make a qubit. That's the message I want to deliver. So,
excuse me, can you?
Yep.
This picture now, the cross is what? The cross is the.
Sorry, I told you the symbol is important, but I changed the symbol. Sorry, this is the junction and capacitor, and this is the inductor.
Good. Now, if you can go back to the previous.
Yep. Here.
Experimental picture there.
Which is this one?
So where is what here?
Where is what?
Where is what? Where is the junction itself?
Okay. So, you know, aluminum is the superconductor. And if at first on the silicon wafer, we evaporate the aluminum. And after some time, it will be oxidized, right? So there is a thin aluminum oxide film. And on there, we deposit another aluminum. then it naturally becomes aluminum, aluminum oxide, aluminum. So this is the junction.
So where is the geolocation of the junction itself? Can you point it? with your finger?
This is the junction.
I think.
I think, yeah, this part is the
I'm trying to
very junction.
I just understand all
Yes, yes.
These Hamiltonians you show the inductive term and the capacitor. Where are they in this?
Okay, I will show you later. Yeah, it is just a junction, only junction. So
It has everything in it in a sense, right? It has a
that's true, but to make a superconducting qubit, we need a relatively large capacitor. So that junction itself is not enough to make a qubit. So in general, we put the capacitive pad and we connect these two pads using the junction. So this is the basic structure of the superconducting qubit. Yeah.
Why don't you use niobium? I remember quite often people use niobium. Why aluminum?
Aluminum is easy to fabricate. That's the reason. So when you make a capacitor pad, we actually, most of group using the niobium for this pad. But for junction, because of the practical issue, people usually make a junction with the aluminum.
So the transition temperatures of both can you remind us?
No, actually, yeah. Actually, I'm an optics guy. I would say I'm an optics guy, so I don't remember the number exactly.
Okay.
I like when you Google it.
Sorry, I have also a question. I fail, can you go back one? I failed to get what did you, I mean, before you were having, let's say, all the levels spaced by omega r. So if I understand correctly, that was not a qubit because, let's say, the transition from 0 to 1 was the same of the transition from 1 to 2. So, okay. Now, what did you get? So now omega j, so the transition from 0 to 1 is, I mean, in that figure, there is no omega r anymore?
Yes. So as you can see, the level is slightly changed. So yeah, it is close to omega r, but it is not exactly omega r. So just if you think we quantize, I mean, we find the eigenenergy of this system, then there is an eigenvalue which corresponds to the each energy level.
Correct.
And that is the first transition gap is the omega j. That's what I'm calling.
Okay, and the others are different.
They are different. That's what I'm calling as unharmonicity.
Shouldn't be very much larger, such that, let's say, the transition from 1 to 2 is very hard because 2 is very high energy?
That's possible. We can sculpt the Hamiltonian as we wish. So we can give a very big unharmonicity, or we can reduce the unharmonicity as we wish. So we have every tool to control the Hamiltonian.
Okay, but what is better? Is better to have a larger?
That depends on the situation. I don't prepare the slide. So at the beginning of the superconducting circuit, there is a very short coherence time because of the charge noise. And if you assume there is a big unharmonicity, then it becomes very sensitive to the charge noise. So it reduces the coherence time. That's why people are considering this small unharmonicity in general. So if we adapt this parameter regime, then it can suppress the charge noise.
I see.
Yeah. So using this way, people achieve 100 microsecond or above that.
So this unharmonicity is enough to suppress the transitions from 1 to 2 that you don't want?
Yes. Unharmonicity should be finite number. Okay. And this unharmonicity is bad for fast quantum gate. So if we consider the very fast quantum gate, which is made by a short pulse, if we Fourier transform this short pulse, then it has a broad frequency, right? So it can hit the higher energy level, so it can excite it to high.
Right.
Yeah, so the unharmonicity should be not that small and not that big. So there is a sweet spot.
I see.
Yeah, in the parameter region. Yep. So yeah, as I said, there are many ways to implement the superconducting circuit by changing the circuit parameter. And I'd like to categorize the way using these two companies. So yeah, IBM and Google are the leading company for this system, and they are taking different strategies. So in case of the IBM, they are using the fixed frequency qubit. So the element is the fixed Josephson junction and capacitor. And in case of the Google, they are using the frequency tunable qubit. So if we use the squid instead of the single junction, then we can control the effective Josephson junction because of the interference between them. And by controlling the external magnetic flux, then we can control the system's frequency like that. But each strategy has its own advantage and demerit. The merit of the fixed frequency approach is that because this is robust to external flux noise, and it has a smaller dissipation channel, so we can achieve very high coherence time. But in case of the Google, even it has a frequency tunability of the system, because of the dissipation channel, like this one, and because this system energy depends on the magnetic flux, so it is vulnerable to the flux noise. So that's why it has a smaller coherence time compared to this approach. But as I said, the frequency tunable approach has its own merit. That is, frequency tunable architecture has more interaction types. So for instance, let's consider two qubit system. And if we tune the one qubit's frequency, then we can implement versatile interaction between them. And that is the reason why most of interesting quantum simulation has been demonstrated in frequency tunable architecture. But I have to note that this simulation also can be implemented in the fixed frequency architecture, but it would be inefficient. Yeah.
They have a complete set of gates.
Yes, sure. So the merit of this feature is it is easy to make a versatile quantum gate, or you can consider it kind of analog quantum simulation. So it is good for more general purpose. Even in case of the fixed frequency architecture, there is a universal quantum gate set. But yeah, the variety would be limited compared to this frequency tunable.
But if it is universal, then the variety is not limited.
That's true, but
I think apart from the number of gates.
yes, because we always need to consider the number of gates because of the coherence time. Yeah. So versatility, I mean, the variety is generally good if we want to implement the quantum simulation or algorithm.
So in this Google one will be better to have multiple qubit gate?
It is hard to say because multiple qubit gate is start to be developed recently. So I don't know which system is better. And actually, I want to discuss about it later. So I will show you how to impose the frequency tunability to the fixed frequency qubit system. If we use my architecture or my protocol, then I think both systems has the similar power. I will show you later. So yeah, there are some challenges in superconducting devices. The first is the trade-off between robustness and tunability, as I discussed so far. And the second challenge is the connectivity. So this is the transformer qubit, superconducting qubit. As I told you, these two paths work as the capacitor, and Josephson junction is placed in between them. So this is the superconducting qubit. Yeah, and as you can see, each qubit is connected with the nearest superconducting qubit. So the interaction range is accordingly limited. So it is hard to make a multi-qubit interaction.
Can you define the robustness? Because it could be.
Yeah, robustness can be understood as the coherence time. So as I told you, fixed frequency architecture has a longer coherence time.
Oh, coherence.
Yeah.
So it's protection against the coherence.
Yes, yes.
What about fidelity? Fidelity of gates.
That two property go along. each other. So higher coherence time has a generally higher fidelity, because recently most of quantum gate is limited by the coherence time. Yeah. So about these two challenges, I will present two solutions. This is not the ultimate solution, but I will give you some possibility to overcome that. The first is how to make a 3-qubit gate using 2-qubit interaction. And the second is how to impose the frequency tunability to the fixed frequency architecture. So let's start from this 3-qubit gate. I think most of you are not familiar with the quantum gate, so I prepared this. So Toffoli gate is also known as the control not gate. So basically, let's say A, B are control qubits, and C is the target qubit. And the functionality is when the control qubits are in 1-1 state, then target qubit is flipped from 0 to 1 or 1 to 0. So that is the function of this Toffoli gate. And this Toffoli gate is a key element of a universal reversible classical computing. Here, universal means if we compose the Toffoli gate, then we can make every Boolean operation, every possible Boolean operation. And similarly, this Toffoli gate forms a universal quantum gate set with the Hadamard gate. And here also universal means we can implement the O unitary by composing Toffoli and Hadamard gate. Even this gate is very powerful, but it hasn't been deployed much in real experiment because it's hard to make it in a native way. And if we try to make a Toffoli gate by using a bunch of single qubit gate and 2-qubit gate, then it it always has a lower fidelity. So that's the reason why we cannot use this Toffoli gate in real experiment. So there are several trials to implement the Toffoli gate in each system, but that wasn't very successful. So the fidelity is about 87, it's like around 90%. So not enough fidelity to use in quantum simulation or quantum algorithm. So
in the experiment you use physical qubit or you use logical qubit?
So yeah, it's a physical qubit. Yeah. So if you say the logical qubit, that means error correction code, right? Yes. People don't have a good logical qubit yet. So in my talk, every qubit means physical qubit. Yeah.
So can you estimate like the error that you can get after a few operations?
Yes. So basically, you can just apply the power to this fidelity. Yeah, that approximately, yeah, same with the expected outcome. So I tried to make a Toffoli gate, but I realized that Toffoli is more natural in this superconducting system. So let me explain how I can implement this later. And before that, let me point out what is the difference between them. So the only difference between Toffoli gate and Toffoli gate is when the target qubit is flipped, conditioned on the control 1-1 state. In case of the Toffoli gate, it acquires additional phase shift. That's the reason why I call this gate as the Toffoli gate. So yeah, let me explain how we can implement the quantum gate in physical system. Basically, the quantum gate is the unitary. So as we can learn from the textbook, the unitary can be designed by engineering the Hamiltonian. And by propagating the system, then we can obtain a certain unitary. So for instance, if the Hamiltonian is given in this form, and after a certain duration, it becomes a certain unitary, right? And this has a one feature that if the Hamiltonian terms are commute, then we can decompose the unitary into separate two unitary, which is determined by each Hamiltonian term, and they are interchangeable, right? So let me consider the experimental situation there are 3 qubits, and each qubit is connected in a linear chain. And to activate the interaction between Q1 and Q2, I can apply the drive for Q1 with the Q2's Lagunas frequency. That's the reason why I call this as the cross Lagunas. If we use this effect, then the Hamiltonian, interaction Hamiltonian is given in this way, and the Hamiltonian interaction amplitude is controlled by the drive amplitude. And additionally, if I drive additional drive for Q3, then we make another 2-qubit interaction. And even we apply this 2-qubit interaction simultaneously because these are commuting. So yeah, we can consider this unitary is not a non-trivial 3-qubit gate. Instead, this is just sequential operation of the 2-qubit interaction, 2-qubit gate. So my idea to overcome this is adding a non-commuting term. So it is easy to implement because this is just a local operation. So if we drive the Q2 on lagently, then I can add this non-commuting term into the Hamiltonian. So I would like to say this non-commuting term take a role like a adhesive glue. So it makes this operation becomes non-trivial 3-qubit gate. So so our target gate is this Toffoli gate.
Can you come back to the last line? How can you make the last operation? Because I thought that if the frequency of Q1 and Q2 are similar, then if you apply to the second qubit, it will affect both the Q1 and Q3. But is this correct?
That's not true. So basically, this is the capacitive couple, and Hamiltonian is so it's like a dipole interaction between 2 atoms. Okay. So and there is only nearest interaction. So this cross Lagunas effect comes from that term. So this will not affect the other qubit. And these 3 qubits have different frequencies. And so our target gate is this Toffoli gate. And for experimental convenience, I implement the controlled NOT gate for 0-0 control state. So when the control states are in 0-0, then target qubit is flipped. That's my goal. So we need to implement the 2 types of operation for the target qubit. When the control qubit are in 0-0, we need to apply the bit flip operation for target. And for the other case, we need to apply the identity operation to the target qubit. So there are many ways to implement such operation. If we look into the bit flip operation, we can consider the pi rotation from 0 to 1, or 3 pi rotation, or 5 pi rotation, or so on. And for the identity operation, we can consider doing nothing, or 2 pi rotation, or 4 pi rotation, or so on. So there are so many possibilities to implement this Toffoli-like gate. I studied some possibility, and I found that this combination, 3 pi and 2 pi, give the shortest gate operation time. So I decided to implement this combination. And what I need to implement in the experiment is this conditional Rabi frequency condition. Only when the control states are in 0-0, I need to give a 1.5 times faster rotation than the other case. So this is the Hamiltonian, what I told you before. So to study the conditionality, I obtained the effective target Hamiltonian using this equation. So for instance, if we consider the control state 0-0, then the eigenvalue of this G and this G operator is +1. So this Hamiltonian can be reduced as the alpha x plus beta x plus so on. So this is that one. And if we consider the target state of 0-1, then the eigenvalue of this is -1. So it is minus beta x. In this way, I can obtain the all effective target Hamiltonian. Yep.
What is the t there? Is it like multiplied by time, or because you mentioned before time was exponential, right? So I wonder.
I don't understand the question. Can you repeat it?
I wonder what is the lower index t? Is that time?
Sorry. This is the target, and this is the control 1 and control 2.
But you run this for some time, right, to get the
So I will consider the time-independent Hamiltonian. So with this time-independent Hamiltonian, I will propagate the system.
for some fixed time.
Yeah, for a certain duration.
And given the time, you will reach the topology.
Yes, yes. So I will rotate the target. And as I told you, to make a bit flip operation, I need to rotate the system with a certain angle, like a phi or 3 pi. To achieve this rotation angle, I need to specify the gate duration.
Oh, I see. So you can choose specific alpha, beta, gamma based on.
Yes, to make this and additionally the gate time. Because with the alpha, beta, gamma, delta, I will only determine the Rabi frequency. After that, I need to propagate. Yeah.
Okay, with a multiple of the Rabi frequency that is determined by alpha, beta, and gamma and so on.
Yes, actually, alpha, beta, gamma, delta are determined by the drive amplitude and drive phase.
Right.
Yeah.
Okay. So you just need to match all these to like multiple of 5.
Yes, that's true. Yeah.
So can I question that? Can you please comment on the resonance of frequencies of the control qubits? Is it that far from the omega's t, or?
So basically, each qubit are detuned about 100 megahertz, and its own frequency is like a 5.1 gigahertz and 5.2 gigahertz, 5.3 gigahertz. And I drive the qubit with the 5.2 gigahertz to make a cross-resonance effect and on-resonance driving for all qubits.
I question, is there any phase does not change? How to control each gate phase, some phase?
So because the phase always has an arbitrariness, so I can define the phase in experiment. So I will call this is the phase 0. So I can define the phase individually, and the tuning parameter in experiment is the drive phase. So basically, this drive is the sine function. So by changing the microwave phase, the sine function, then I can determine the Hamiltonian's parameter. Like if I set the phase of this drive as theta, then this gamma is given as a cosine theta, and delta becomes sine theta. Yeah, so it just defines the angle of the between x and y. Yeah, so we have this effective target Hamiltonian, and as I told you, I want to make a conditional Rabi frequency to satisfy that the target qubit rotate 1.5 times faster with the control 0, state than the others. The first step is making these 3 Hamiltonian give the same Rabi frequency, and it was easy to achieve. If I set the beta and gamma as the alpha, then the Hamiltonian becomes like that. So if I write down the conditional Rabi frequency, then it is like this. So additionally, we have one more degree of freedom, delta. So by setting this delta to be this value, then we can achieve this condition. So experimentally, I measure the Rabi oscillation. So by sweeping the drive duration, so as I said, the Hamiltonian is fixed, and I just want to see the state evolution. So when I prepare the control state is 0, 0, then the target qubit rotate 1.5 times faster than the other cases. And if I set the gate duration at this point, 353 nanosecond, then it becomes the I-topology gate. And I didn't tell you why it is the I-topology. So I like to explain this with this picture. So basically, the state evolution on the Blow sphere or Hilbert space make a geometric phase, right? So I can say this is the Panchanatam Berry pace. So if the state evolved like a 1 pi rotation, then it acquires I phase shift. So 3 pi rotation gives a I to the 3, so it becomes minus I, and it gives a -1. So if we count the -1 as the global phase, then there is a I phase shift for this bit flip operation. That's why it is the I Toffoli gate. And I benchmark the gate with this truth table. I prepare the input state as the computational basis from 000 to 111, and I measure the output probability, and it gives the good Toffoli gate picture. And this way, we cannot measure the phase shift term. So I leverage the other technique, which is called the cycle benchmarking. So using this technique, I can get a very high fidelity. So this is the 98.3%, and I would like to say it is deployable for real quantum simulation or quantum computing.
Can you fix the I by employing a phase shift? Is it like simple? Like make the I Toffoli by employing like a single qubit phase shift?
That's a good question. But unfortunately, we cannot shift the phase using a single qubit gate only. We need 2 qubit gates.
Oh, because only some things are shifted by I, but other things.
Yes, yes.
You are using what K to sequentially if the fidelity is multiplied. Right?
Approximately that's correct. So if we apply 2 times, then the fidelity will be about 96, like that. Yeah.
So you mentioned that this gate time takes about 300 nanoseconds to implement, but IBM has like the coherence time like 400 microseconds, so you can make about 1,000 of these operations during the coherence time of IBM.
Yes, and that's true. Yeah, but it depends on the expect quality of the lesion, because if you consider if we apply the gate during that time, then means exponential give like a 66% fidelity. I mean, yeah, the quality is not so good if you apply the gate that much. So that's why IBM consider the error mitigation technique, even they have a relatively
What do you mean? Like if you apply it sequentially, the fidelity goes down.
Yes.
Yeah.
Yes. And I experimentally confirmed that this fidelity limitation comes from the decoherency path. Only, mostly from the decoherency path.
Does this surpass the threshold for error correction?
Actually, I don't know, because most of the error correction fidelity is studied for the 2 qubit operation or single qubit operation. So I don't study in that direction, sorry.
Okay, and is I Toffoli still universal?
Yeah, I Toffoli is a universal, and I have studied that part in the paper, but I don't bring the thing in today's talk. Yeah. With the I need the additional Hadamard gate as like a Toffoli gate. Yeah.
Right. So yeah, one question from I think I missed some points that about the origin of this the coherence. Is it due to some charge fluctuation in this capacity coupling? What is it?
There are so many mechanisms which induce the decoherence. As you said, there is a charge noise and flux noise, or there is a dielectric loss. So the E field is oscillating in this system, and it interferes with the dielectric surface, which is not a superconductor. So this dielectric material absorbs some energy, and it limits the T1 time. I think that is the most dominant mechanism of the loss. And additionally, the quasi-particle is also a big contributor. So currently it's not a big contributor, but there are 2 points. The first one is because of the system is not absolutely zero, so there is a fluctuation due to the quasi-particle population. And additionally, the radiation comes from the outside, also break the Cooper pair, so it also reduces the coherence time. So there are several mechanisms in the coherence.
Due to the, if I understand correctly, you mentioned the two, the thermal fluctuation and
the radiation. Yes. Yeah. The main source is the dielectric loss currently. Yeah.
You mean that there is some energy exchange between the
dielectric loss? Yeah, means that exchange with the dielectric surface, the silicon surface or sapphire surface. Yeah.
If you lower down your temperature, then can you reduce this coherence effect with the?
Yeah, that's true. That is because of the particle density. Yeah. And also this system is coupled with the other coupler, like for lead out, we need an additional coupler, and there is a thermal photon. If then this lead out resonator is always coupled with the qubit. So because of that, this thermal photon induces some dephasing effect. So we always need to reduce the temperature to avoid this situation.
So is the fidelity also depends on the temperature?
Yes, that's true. Yeah.
Thank you.
Maybe we will try to make the input is a superposition.
Sure. Yeah. So this is just the basic test. So to do this, we need to prepare the input very many way. So yeah, this is the believable.
And the fidelity also good if you do the.
Yes, the meaning of this fidelity, it is called as the average gate fidelity. That means so the definition of the average gate fidelity is like this. So we put the every possible input state, so like a complete input state set, and measure the transfer state fidelity. And if we average the transfer state fidelity, then that is the definition of the average gate fidelity. So if we put some certain input state, then it would give a better fidelity. But for the other input state, then it would has the lower fidelity. So this is the conclusion. So in this work, I demonstrate the deployable 3-qubit gate. And in this work, I provide new paradigm of multi-qubit gate implementation. So for instance, if we want to make a 4-qubit gate, then we can use the 2-qubit interaction in sequential, and by adding the non-computing term, we can make a non-trivial gate. But I don't know if this is powerful or not, but yeah, this is one way to make a multi-qubit gate using 2-qubit interaction. And I will skip this. So this shows just the application of IEEE gate. Yeah, IEEE gate was good. And the second topic is the programmable Heisenberg interaction for fixed frequency qubit. So yeah, let me explain the Heisenberg model first. I think all of you are very familiar with this. So this model assumes the interaction between the near-least spin, and the interaction is written in this way. And this interaction can be divided in two parts. The first is the spin exchange interaction, and literally this interaction make these two spin states are exchanging. Like an up-down state can be changed by down-up by this interaction. And for this spin-spin interaction, GG interaction, this make the Lamour frequency of the first spin is affected by the other spin state. So it just changed the rotating spin. So this Heisenberg model has been the important workhorse to study many-body physics. So it has been used for studying phase transition of many-body system or phase transition of spin transport, and it is used to reveal the anomalous spin transport. When we studied this, the anisotropy of the system is the key parameter because it is working as the order parameter of the phase transition. So we need a programmability of this JXY and JGG. So that's the requirement to study such physics. I will explain how to implement that. Before that, yeah.
Sorry, earlier Hamiltonian, interaction is nearest neighbor or?
Nearest neighbor.
Yes.
Yeah.
And it is into the, you are considering the 2D case, the two-dimensional case?
Yes, but I will consider only 2 qubits in our work.
Okay.
Yeah. So this is just yeah, you know. So the way to implement the spin exchange interaction is like this. So let's say there are 2 qubits, and each qubit, each spin has 2 different transition energy, and when the transition energy are the difference between that transition energy is bigger than the coupling strength, then there is no effective interaction between them. But if we bring up the first spin's energy to be resonant with the second spin, then they start to exchange their population, and you can understand the physics as the Rabi oscillation between 0, 1, and 1, 0 state. So like that, and the Rabi frequency is determined by the coupling strength J. Yeah, as you can see from the previous explanation, we can implement the XY interaction using the frequency-tunable qubit. But as I told you, the coherence time is limited. So if we can make such XY interaction in the fixed frequency qubit, then we can take advantage of the high coherenceness, and we can simulate more quantum simulation, more versatile quantum simulation, right? So my question is, how can you make the frequency-tunable qubit tunable? So my approach is this. So I consider this situation, the fixed frequency qubit is under microwave drive. So in my formalism, I will consider the fixed frequency qubit has a 2 level. So I can write out the Hamiltonian with the Pauli G operator, and the energy gap is omega q. And the interaction with the microwave can be described by this Hamiltonian term, Pauli X, and the drive amplitude and the drive frequency is given in this way. If I try to write down the Hamiltonian energy using Schrödinger equation, then I will fail because this is the time dependent Hamiltonian. But this Hamiltonian has a time periodicity, so I can use the Ploquet formalism. So I can rewrite the Schrödinger equation in this Ploquet energy, and I can define the Ploquet state and Ploquet energy. One good thing is Ploquet energy is time independent. So, and this Ploquet energy depends on the drive parameter, so it is easy to tune. So for instance, if I tune the drive frequency, then I can manipulate the Ploquet energy, and the drive amplitude also can be used to tune this way. So in this way, I can impose the tunability to the fixed frequency qubit. So before showcasing my experimental result, I have one thing to discuss before. That is synthesizing Ploquet qubit in real system. So basically, the system is working in the barrier state. Without this drive, the system exists, right? So let's say the barrier state is given as an A0 plus B1, this superposition state. And if we want to turn it on the Heisenberg interaction, then we need to ramp up the drive amplitude, right? And during this procedure, we want to keep the adiabatic process because we don't want to lose the quantum information. Yeah.
I just missed something. So are you saying that this time-dependent Hamiltonian is equivalent to having 2 qubits with that spin flip interaction?
No, this is just a single qubit story.
Okay.
Yeah.
So how by tuning the Ploquet states, how are you changing the Heisenberg interaction? What, like, I just didn't get that.
So you are asking why it is tunable, right?
No, I'm asking how do you connect this picture with the earlier Hamiltonian that you wrote in terms of JXX and ZZ?
Okay. Now, my quick answer is, as I show you for the XY interaction, if I make these 2 systems be resonant, then it starts to exchange the population, and it is the XX plus YY Hamiltonian.
I see. So you do it for 2 of the qubits.
Yes, I will do it for 2 qubits. So yeah, so to keep the quantum information during this mapping, so this mapping should follow the adiabatic process, right? So to do that, I need to lamp up very slowly. And as you can see from here, the Bayer bases 0 and 1 and the Ploquet bases are not aligned. So yeah, there is a possibility to excite to U1 or something else, right? And then after this interaction, I want to return it back without any change. So it also should follow the adiabatic process. So the simple scenario is like this. At first, I prepare the initial state as 0. And if this lamping process follows the adiabatic process, then it will be mapped to U0 and it will going back to 0 state, right? And if the lamping time is too short, then this becomes a diabatic process, and there is a possibility to transit to the another level. So yeah, it becomes like a superposition between U0 and U1 basis, and after that, there is a leakage to the 1 state. So experimentally, I measure the leakage to the excited state. So as I said, if the lamping time is long enough, it follows the adiabatic process. So there is no leakage to the first excited state. But if the lamping time is short, then there is a leakage to the excited state. And the reason why this is oscillating, the population is oscillating, is because of the dynamic phase, which is accumulated during the state is in the Ploquet basis. Yeah, but this is bad news for our protocol, because to activate the Heisenberg interaction, we need to spend like a 120 nanosecond time to meet the adiabatic condition. So I tried to find a way to reduce the this mapping time. So the solution was shortcuts to adiabaticity technique. So the concept is very simple. So this is just a conceptual image to explain this STA, shortcut to adiabaticity. So the x-axis is the Hamiltonian parameter or control parameter, and y-axis is the energy. So if we change the control parameter slow enough, then the third level energy follows this line, and it keeps the energy level during the transition, right? And if the parameter is changed rapidly, then there is a transition between each level, and this is the diabatic process. The concept of the shortcut to adiabaticity doesn't care about what happened during the procedure. What it only cares is that the final energy level. So if the final energy level is matched with the initial level, then we are fine, right? So this is the key of the STA technique. So there are many techniques to make this shortcut to adiabaticity, but the most famous technique in superconducting qubit is the drag derivative removal by adiabatic gate, because it is easy to implement in experiment. So let's say if we want to apply this lead envelope pulse, what we need to do is just applying the first derivative of this envelope with the 90-degree phase shift, this blue one. And the optimal condition for the amplitude of this derivative envelope can be found by sweeping the amplitude in the experiment. And it is very easy. So this is the experimental result. Here, the drag coefficient means the relative amplitude of that derivative envelope. And here, 0 means we are not using the drag technique. In this case, we need a 60 nanosecond lamping time to achieve the adiabaticity condition. But if we use the drag technique at a certain drag coefficient, we can reduce down to 30 nanoseconds. So in this way, we can make it fast. We can make the protocol fast. And I will show you how I implement the Heisenberg interaction between these two fixed frequency qubits. So there is a single junction. So this is literally fixed frequency qubit, and this is connected with the fixed coupler. So there is no tunability in this system. And the first target is that this spin exchange interaction. To do that, I use the P1 and P2. And P1 has a frequency that LED shifted from the Q1's resonance frequency. And P2 has the frequency that blue shifted from the Q2's resonance frequency. So as I said, to make an XY interaction, I need to make them have the same frequency. So with the experimental parameter, I simulate the pocket energy. And as you can see, by changing the drive amplitude, we can tune the Q2's energy like that and Q1's energy like that. And at a certain drive amplitude, their energy become resonant. So this is the experimental result. As I said, at a certain amplitude, this 0-1 state is oscillating with the 1-0 state. And this graph shows the cut image of this line. And this shows very high visibility in the oscillation. That means our protocol is very working well. And I derived this relation. And what this relation tells is that we can achieve the JXY become similar with the J by setting the drive parameter properly. And I implement the spin-spin interaction using the P1 and P3, which have the same drive frequency. So we can define the phase difference between them. So there is a two knob to control the drive amplitude and drive phase. By using these two parameters, I can see that we can control the GG interaction strength. And it has a cosine dependence on the drive phase. And additionally, I implemented GG with the XY interaction, and it also still has a tunability. That means if we fix the XY interaction strength, by changing the GG interaction, we can control the anisotropy between JXY and JGG. So I experimentally implemented various Heisenberg Hamiltonian with different anisotropy. The first is the XX Heisenberg Hamiltonian, but there is no way to benchmark the Hamiltonian. Instead, I made a representative quantum gate, and using the standard technique to benchmark the quantum gate, I can achieve I can obtain this fidelity, and I do the same thing for Ising Hamiltonian and isotropic Hamiltonian, and this also gives the high fidelity. And I also extend my work for the higher energy level, and it also gives a good result. And yeah, good result. And one more thing to discuss is this, because our system is under drive, so the coherence time would be affected by the drive. So I have studied this. So I estimate the T1 energy relaxation time and the dephasing time by sweeping the drive amplitude. And as you can see, the T1 increased while T2 dephasing time decreased. So I like to say this is the induced decoherence by the drive. So to study this more, I studied the heating effect. So to obtain this experimental result, I prepared the initial state as the 0, and I applied the pulse for a certain duration. Then after that, I measured the excited population at the end. Then that means how this drive induced the heating to the system. So this is the experimental result. And yeah, the higher drive strength give the higher leakage. That means there is a larger heating for the higher drive amplitude. And this is the reason why there is a T1 increase and the T2 decrease. And I also tried to understand why this dynamic heating happened using the Lindblad formalism. So this is the basic Lindblad operator to describe the T1 and T2. So by changing, because our system is defined in the Floquet basis, so I rewrite this Lindblad operator in Floquet basis. So in this way, I can explain why there is a dynamic heating. So to sum up, this decoherence induced by the drive is acceptable. I mean, the decoherence is not so big, and this decoherence effect can be explained to some extent by the Lindblad formalism, which means that if the Lindblad amplitude is small enough, or the system has a good coherence, then the induced decoherence also be small. And this is the conclusion. In this work, I demonstrate the best blockhead qubit synthesis using a shortcut to adiabatic technique, and I demonstrate the programmable interaction for high coherence fixed frequency qubit. And I want to summarize my work with this image. There is always trade-off between the tunability and robustness, but I find a way to impose the frequency tunability to the fixed frequency architecture, which has a high robustness. So in this way, I can achieve the tunability and robustness simultaneously. And I expect if we apply our scheme to the cutting edge platform, like a fixed frequency platform, which has more qubit and which has a longer coherence time, then I expect we can explore many fascinating quantum many-body stuff. Thanks for listening. This is just a summary page. So I discussed about this technique and this one. Thank you for listening. Yeah.
Two questions. The first one is the driving that we considered was a sinusoidal drive, cosine omega t.
Yes.
So what if I just consider a simple linear in time, like Landau-Zener type Hamiltonian? Because in that case, I know all the probabilities and maybe I see for this 2 by 2 Hamiltonian.
Why you want to consider that?
Because I think in your case, all you want to do is that you want to have a controllability. You want to know all the states and how they are going from one state to another state. And if I just have a linear time dependence, then I know how all the states are going where, like if all these matrix elements, etc. I know.
I think if we make a system like that way, then I don't know. It's more like a DC effect for this system, right? Because the characteristic frequency is very low compared to the system's barrier frequency, like a 5 gigahertz. So I didn't think about that DC effect, but in this blockhead formalism, the key is making, if we use this blockhead formalism, then detuning should be small enough. If not, this is just a non-resonant driving.
Between what and what?
So the qubit frequency is defined, and the detuning means the detuning of the frequency of the drive, and the detuning means the difference between qubit frequency and drive frequency.
I see.
Yeah, if the detuning becomes larger, then all interesting physics goes away, because I can say this light and atom doesn't interact strongly.
But if I have just a linear dependence in time, then there is, it's not a sinusoidal term, so there is no, I don't see how you can get a detuning. Just like if you go back to your Hamiltonian, the one that you wrote before.
Yep.
Yeah, all I'm asking is that instead of, no, after that.
This one, right?
Yes, all I'm saying is that instead of having cosine of omega t, you just write A times t.
Yes. Maybe you would be right, but I don't think about that much. So what you're saying is, let's say, even if we consider the fixed A, right? So if we diagonalize this Hamiltonian, what you mean is the energy gap can be tuned by the A. That's what you're saying.
Yes, yes.
Yeah. I don't think about it. Yeah.
Okay. And then other question that I had was, so you consider your scheme, by your scheme, you can tune the interaction between two qubits.
Yes.
So now, theoretically at least, if you have, let's say, small number of qubits, not too many, and then I can have all-to-all connection.
Yes.
Can I know?
So in superconducting qubit, we only consider the nearest interaction
Yeah.
because of the limited connection. So yeah, you are thinking of this situation, right?
Yeah, I'm thinking of like putting them on a ring and then having some sort of like all-to-all connection.
Yeah,
That is possible.
we can make it, but the scalability will not be good. So the idea is like just making a capacitor between the qubit, then it induces the dipole coupling between them. So the capacitor can be considered like just a electric wire. So make an electric wire between them, an electric wire between them, and we can make an electric wire between them by jumping at here. So in this way, we can make a all-to-all connectivity, but this is not a scalable way.
Okay.
Yeah. Or there is another approach using the parametric scheme, but I will not talk about it now.
I also, you wanted to make your lattice. Your interaction tune is simultaneously in all lattice.
Yeah, that's true.
This is in your method, is it possible you try the very simple case is 3
Yes, yes. So for instance, if we drive this 3 qubit with the Oblation driving, then for instance, let's say if we tune the Floquet energy of this 3 system becomes the same, then they start to interchange. I mean, they start to exchange their energy, and it is described by this equation. So just applying the microwave simultaneously, ideally we can impose this Heisenberg interaction between them.
I have a short question about this dynamical heating mechanism. Actually, I don't know whether this effect, but if possible, can you convert this your plot to the temperature? Whether it is significant or
Oh yes, it's easy to convert to the temperature, but the problem is that depends on our theoretical model, right? Yeah, so I don't know how to. I mean, yeah, we can define the temperature based on this heating effect, but I don't know the exact meaning of that temperature.
I see.
Yeah, because I think this happened because of the basis change, so it did not be a clear temperature.
I see.
Yeah.
For example, can you repeat your experimental data with some effective Bose-Einstein distributions?
Yes, people usually model this T1 with this heat bath model, but in this case, I don't know. Something different happened.
So this dynamic heating effect is also apparently, for example, the readout experiment.
Yes, that's true. So this heating effect can happen during the lead out time. But in our case, the lead out time is fixed. So you can consider that a contribution from the lead out are the same for all the measurement.
Thank you.
Here is also question you're applying the only sigma x operation.
Yes.
Sigma y operation.
That's possible, and that is, as I explained in my first talk, I told you if I change the drive phase, then it becomes a sigma y operator, or the combination of the sigma x and sigma y. So what we need to do in experiment is just changing the sinusoidal space. In that way, we can control it.
Simultaneously. spectra and sigma 1.
Yes, for each frequency, we can define the different phase.
Also, if we are tunable, you know the general Hamiltonian between two spin, right? This x-axis is a simple case, right?
Yes.
For example, is the gyroscope-Moria interaction also possible, or off-diagonal interaction is also possible. And do you think about this interaction can be applied?
To be honest, I don't know what is that interaction. What people usually consider in experiment is there is a limitation in the system, right? So there is a finite tool set. And what people consider as the totalization of the unitary. So by totalizing the specific unitary and by interleaving certain operation, because of the non-commutivity, we can implement a very exotic interaction. And it is called like a digital quantum simulation. And in this way, I think we can implement what you said. And this is the typical Hamiltonian, which happened in the superconducting qubit.
Do we have any further questions from the audience? Let me maybe ask, so you've shown these high fidelities that you get. Can you comment what was the typical number of measurements that you did to get these estimates?
So that depends on the gate, right? So I want to advertise my leisure that so far there was no way to implement such I-swap gate or swap gate in the fixed frequency qubit region because there was no way to induce the frequency tunability, impose the frequency tunability. So before in the IBM architecture, people implement the I-swap by using a 3 CNAT gate. So inevitably the fidelity is limited. So I would say it's less than 97-ish. So it is higher than those approach. And this one, I told at the beginning, I showed that people try to make a topoly gate and the fidelity is about 90%-ish, right? And using my technique, I decompose the topoly gate using the Q-tree gate. And in that way, I can achieve the 96% fidelity for topoly or control Z gate. So this tells how this protocol effective.
But what is the number of measurements, for example? So for this example,
you mean like the triers, the number of triers?
Yes, for example.
So we measure this fidelity for 1 day. We repeat the measurement for during 1 day, 24 hours, and the fidelity wasn't fluctuate much. But there is a possibility that TLS, traverse system defect, interact with the system, then the coherence time suddenly drop. In that case, the fidelity would be very worse. If not the case, the fidelity can be kept for a long time.
But in this 1 day, what is this 1 million of measurements or 100 million or 1,000?
You're talking about the shots or?
Yes, yes. Just order.
Yes, just for each point, it's hard to tell because, okay, to get a population, the probability expectation value, we are using the 10,000 shot for each probability estimation. And to get each data, we did a lot of experiment to learn certain protocol to benchmark the gate. And if we take into all measurement, then the shot will be very huge. Yeah.
Okay.
Generally, to get this one plot, it takes like 30 minutes. Yes.
Okay, thank you. Do we have other questions? In case not, then let us thank Yosep again for this excellent talk. And thank you all for joining.